So we said true error is equal to the true value minus the approximate value, or relative true error is the true error divided by the true value, gives you a sense of scale and magnitude. But I'm going to claim the following, that true error does not make sense. Why is that? Yeah. Okay, so I want to invert your answer. I want to say, yeah. Exactly. If you have the true value, why are you computing an approximate value in the first place? Right? It doesn't make sense at all. And so that's exactly it. If we know the true value, why bother with computing an approximate value? And that is generally correct. We're going to talk about a different type of error, because in reality, we do not know what the true value of a quantity is when we're doing engineering and scientific measurements. Okay. However, there is still a special case where we actually know the true value, and this is this is part of when you're developing numerical methods or algorithms. You want to test your methods. And what you do, you typically test your ideas and your methods on problems for which you know the true answer, right? So you know the true answer, you bring in your numerical recipe, and you run it, and then you can compare how well your numerical recipe is doing. Now, if the comparison, you're happy with the comparison, then you can say, okay, I'm going to take my recipe and apply it to systems where I do not know the true value. So there's a special case where we actually know the true value, and those are typically concocted problems. We come up with these problems such that we know the exact solution, and then we apply our numerical method and then compare. And that's what we will do in many cases in the class. As we learn about a certain algorithm, how do you evaluate the performance of the algorithm? You want to run it on a system for which you know the true answer. Now, those systems are typically limited in scope. They're simple, because we're able to get an exact solution, but yet they give us enough confidence in the method itself. Okay. Now, in practice, we really do not know the true value. Otherwise, the true value of a quantity, let's say you're measuring, temperature in a complex reactor, we don't really know the exact answer. Okay. So what we want to introduce the concept of approximate error. Okay. So we don't know the true value, but we can get an idea of how to approximate, not the true value, just approximate the error. So we can get a sense of the error that we are committing. And we introduce the concept of approximate error. I'm going to first define it to you, and then we're going to, the definition may be a little bit kind of like, what are you talking about? But then you'll see with practical examples. So just bear with me for a second. Approximate error, we define it as the error between a current approximation and a previous approximation. And I'll define current and previous in a second. So mathematically, we write this as capital E. Remember that the true error or absolute error, we wrote that as capital E, as opposed to relative, where we wrote an epsilon. So capital EA is approximate error, is current approximation minus previous approximation. Now, what do we mean by current approximation and previous approximation? Typically, we mean a higher precision calculation compared to a lower precision calculation. The idea being that our numerical methods will always converge to the exact solution, to the exact answer, if we run them at high enough resolution. If we use a lot of terms in the calculation, whatever that means. And the idea then is that between one approximation and a higher resolution approximation, the difference gives you a sense of the error, gives you at least an order of magnitude analysis idea of what the error is. Okay, so let me give you let me give you an example of what we mean by current approximation and previous approximation. Okay. You will see that pretty much all things we do in computing, we're going to be doing repeated calculations. There's going to be a for loop that runs a recipe that keeps calculating the same formula over and over again. Now, each time you run that formula, okay, you're going to get a value. And this would be your current approximation compared to the previous calculation you did. One specific example is Taylor series. Do you remember what a Taylor series is? I don't need the formula, just a rough, yes, Emily.
The idea of a Taylor series is that you add up a bunch of numbers that follow a pattern, and it helps you approximate the
Function, correct, yes, yes, exactly. So, barring the historical meaning, Taylor series are really powerful in that they allow us to approximate complex functions like sines, cosines, logarithms, etc., using just polynomials. What's a polynomial? Is just a collection of terms that take an independent variable like x, and you add them up. You have x, x squared, x cubed, x to the fourth. Those are really easy to calculate. And the idea behind Taylor series is that you can take complex functions, such as the sine function, evaluated at any x, and then you can express that as this summation, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on for all x. And so, for example, sine 0.1, you just put in 0.1 over here, and then you evaluate the sine function. Similarly, for example, the exponential function is given by this really nice polynomial, 1 plus x squared over 2 plus x cubed over 6, and so on. So again, if you're evaluating the exponential of 2, you just put 2 over here, and then you calculate the exponential, right? Pardon me. That's how calculators actually do it. That's how numerical libraries do it, because what is the exponential? We need a formula expressed in terms of basic algebra, like, products and additions, summations, and divisions, right? And this is such a formula. Now, obviously, we can approximate ex, e to the x, with the first term, but that would be a terrible approximation, right? That would give us e to the x equal 1 for everything, right? That's a little bit silly. Maybe we can add one term, but what if we add what if we do 3 terms, or 4 terms, or 5 terms? Is our approximation going to get better? Yeah, of course. And that's the definition of an approximate error, is that, for example, let's say you're computing the Taylor series for the exponential, up to 5 terms. An idea of the error would be the value at 5 terms minus the value at 4 terms. That will give you a sense of what the error you're committing is. Okay? Does this make sense? Okay, so let's say I ask you to evaluate the error in calculating the exponential using Taylor series up to 15 terms. How do you get the error? Let's say you don't know the exact solution. You can run a Taylor series with 1,000 terms. That will give you a very accurate calculation. And from that, you can subtract the one with 15 terms. So that will give you a sense of the error. Okay? Or you can do the one with 15 terms minus the one with 10 terms. That will still give you a sense of your error. But you have to quantify that error. You have to say, I took the 10 terms, the 15 terms minus 14 terms, or the 1,000 terms minus 15 terms, okay? All right, so the idea, again, is that the higher precision calculation is closer to the truth. So if you do 15,000 terms in this series, that is pretty darn close to the truth compared to a 15-term approximation. Agreed? Okay. All right, so let's actually do this example by hand. And the example says, use the Taylor series to evaluate the exponential function at x equal 2. Use 1, 2, 3, and 4 terms, and report the approximate error in evaluating each term. And this is the formula for ex. Okay. So let's do this one term at a time. So at x equal 2, this is our formula. We're going to start by adding one term at a time. Okay. So if we do one term, the result of the exponential is 1. That's the first term in the series. We don't have an error defined over here, right? Because that's our current approximation, but we don't have a previous approximation. Okay. You could say it's 0, the previous approximation, but that's irrelevant. Okay. So the first calculation doesn't really have a previous approximation because we didn't start. That's our starting approximation. Okay. Now let's add 2 terms. So when we do 2 terms, that's 1 plus x and x equal 2. So that gives us the value of 3. Now what is the approximate error? It's the current approximation minus the previous approximation. Correct? So that's 3 minus 1. And that's equal to 2. Whatever that means, okay, because this is not a relative error, all right? Now let's add 3 terms. So with 3 terms, we're going to add 1 plus x, which is here, which is 3, And then to that, we're going to add 1 over 2 times 2 squared, right? Because x equal 2. And then what is the error for this term? It's current approximation, 5 minus previous approximation. Okay, it's 5 minus 3. That gives you 2. Again, the same value. Now, what about 4 terms? Again, we're going to do 1 plus x squared. We already computed that. That's 5, right? Plus 1 over 6, 2 cubed. And that gives us 6.33333. And then current approximation minus previous approximation is going to get us to 1.3334. So you see the error starts decreasing as we add more terms, as expected, because the more terms we've added, we've obtained a higher precision approximation, okay? And the higher precision approximation is essentially our approximate value of the truth. That's really what we're saying. When we don't know what the true value is, our best approximation of the truth is a very high resolution calculation, okay? Is a high resolution calculation, okay. Again, this is another definition which kind of just discussed, because some people confuse the idea of current approximation minus previous approximation. Another way to define the approximate error is to say it is the difference between a highly accurate approximation or a more accurate approximation minus a less accurate approximation, okay? And we agree that the more accurate approximation is essentially a representation of the truth, okay? And so another example would be what we did last time with the derivatives. And this is asking us, giving us the first derivative if a function can be approximated as fx plus h minus f of x over h for some value of h, where h is some small value. Now, for the function f of x, 2e to the 0.5x, that's what we did last time, find the approximate error in evaluating f prime 3 using h equal 0.5 and h equal 0.05, okay? So now you should be able to tell that the smaller the value of h, the higher resolution or the more precision we have in our calculation. That's the definition of the derivative, if you remember last time and in your high school, that this is the definition of the derivative as h approaches 0. So the smaller the value of h, the more accurate this approximation is going to be. And therefore, we're going to use that value, the value with h 0.05, to represent the truth. And then we're going to subtract the calculation that we do with 0.5. Is this clear? So this would be, when we use h 0.05, this would be our more accurate calculation. And with this one will be our less accurate calculation. Okay, and I'll just punch in some numbers. So for h 0.5, we did that in the previous slides. It gave us the value 5.09. And 0.05, we had 4.53, and we claim this to be our more accurate approximation. It just gives us a sense of the error. We take the more accurate approximation minus the less accurate one. I used an absolute value here. You can use, I recommend use absolute values all the time. And that gives us a sense of the error, okay? So could we have used a value of h equals 0.00005? Yeah, of course. It's just I asked you to do 0.05, but if I ask you to calculate the error, if I give you one value for h and ask you to get an idea of what the error is, say, yeah, I'm going to pick a very small value for h and claim that that's the truth, and that would be the more accurate representation, and then subtract from it the value that I asked you to compute, okay? That's the idea of it. At some point, you will see that the error will not change much as you change h, okay? Now, this again does not tell us how large the error is, okay? So it's just giving us a number, but we have no sense of scale. Again, remember the example of the 1-foot error with the bridge and the table, okay? So what we need is a relative error. And again, we define the relative version of the approximate error. And it's essentially like we did last time with the true error. The relative approximate error is the approximate error divided by, so with the true error, with the relative true error, we took the true error and divided it by the true value. What is the representation of the true value in approximation? It's the higher, the more accurate value, correct? So we're going to take the approximate error and divide it by the current approximation or the more accurate approximation. Because the more accurate approximation represents our truth, okay, the true value. Okay, and that's the mathematical way of presenting it. Again, we're going to use an epsilon for relative errors, epsilon A, to introduce the idea that this is an approximate error, and it's current approximation minus previous approximation over current approximation. Always think of current approximation as the more accurate approximation, the one that has more terms in it, that has, you know, a lower tolerance. It's going to depend on the problem you're dealing with, okay? And typically, we report the relative error as a percentage. So when you say an error is 2%, that's essentially the value of the error is only 2% of the true value of the quantity, okay? All right, so clear so far? It's really just kind of semantics. Okay, so now let's run the same example of the Taylor series and do a relative approximate error. The previous example, we did the approximate error, only it just gave us 2, 2, and 1.3. We don't know what that meant. I want to see a value that has a percent in it. Okay, so again, the same example, we're going to do up to 4 terms of e to the 2 at x equal 2, but we're going to compute the relative approximate error this time. Okay, so we'll present the same layout as we did before. We want to evaluate the exponential at x equal 2 for up to 4 terms. And I have 3 columns here, number of terms, result, and the relative approximate error. Again, for the first term, we don't have a previous approximation, so we're going to let it be. We don't have an error defined over there. You could say the error is infinite if you want, okay? Or well, you don't know what the error is, okay? You don't have to report an error there. But once we have 2 terms, so we're adding 1 plus x. So 1 is essentially in the previous result, plus x equal 2, so that gives us 3. Now we can compute the relative approximate error. That's current value or more accurate value minus less accurate value over the more accurate value. Current minus previous over current. That gives you 66%. Now when you hear 66%, like, okay, it's wow, that's a very large error. Right? It's a very large error, 66%. Okay? Whereas previously we had the value 2. I don't know if 2 is large or small, right? Okay? Now, with 3 terms, we're going to add 1 over 2x squared. So we take 1 plus x, which is 3. So essentially, we're just taking this guy here. And we add 1 over 2 times 2 squared. That gives us 5. Current minus previous over current, 5 minus 3 over 5, gives us 40%. So the error is being reduced, as we expect from Taylor series. It's a convergent series. Because it is convergent, it's going to converge to the true answer. The more terms we add, the smaller our error is going to be. Okay? Now with 4 terms, do the same thing. We're going to add 2 cubed, 1 over 6, 2 cubed, and then our error drops to 21%. And that's pretty great. We expect to have the same trend as we add more terms. Okay, so eventually, once we get to linear systems and nonlinear systems and interpolation, you're going to be using this type of error to report the error in your calculations, okay? But there are other applications that we can use today, okay, just like with the knowledge you have so far in numerical methods. And that's to take the same example, but now we're going to, everything we did so far was by hand. But obviously, in practice, we're not going to do things by hand, because what if I want you to add 100 terms in the Taylor series, and so we don't have the space to do that. We don't have the patience to do that. Instead, we're going to use Python to write a code that uses the Taylor series to evaluate the exponential function at any value of x, but we're going to evaluate it down to an error of 1%. So I'm going to ask, the question is, write a Python code that computes your Taylor series down to an error of 1%. We call that tolerance. Okay, that's the error we are willing to accept in your evaluation of the exponential function. Okay, so how do you think we can do this? Same way we did before. Previously we did 4 terms, right? Right now we're going to keep adding terms until we get to an error of 1%. Okay? So let's get your Jupyter notebooks up and running, and we'll do this together. Okay? So, and I'm gonna turn my back towards you. I apologize, but I want to be able to see what I'm typing. Okay. All right. So let's see. In class, Taylor series relative approximate error. Okay. Oh, it doesn't allow me to put. Okay. Oops. Okay. So just to kind of get you warmed up, you get your notebooks up and running? Anyone waiting for CHPC? Okay. Now, I'm hoping that you went through the slides for EasyPy, where I discuss the idea of modules. So the basic functionality of Python, for those who didn't do that, or for those who did it, just a reminder, the basic functionality of Python does not provide you with useful functions like exponential, sign, factorial, and things like that. Essentially allows you to declare a variable, print it, make a list, do a for loop, and that's it. To be able to use complex functions, and obviously we need to use a complex function here through, if you notice here, through the factorial. So I need to be able to do a factorial of n over here, okay? So I need to import something from outside Python that allows me to use a factorial, and we call those modules. Modules are essentially freely available libraries that define functions that you can use. So one of the key modules we will use here is called the math module. It defines the factorial function, the exponential, sine, inverse hyperbolic, tangent, confluent hyperbolic, ellipsoidal function, whatever, some crazy functions. But it's, some people went up and programmed all of these functions and put them in a module called math. And the way we do this is we import the math module. So you can import the entire math module. And from the math module, then you can use, so you can do, let's say you want to do the factorial, you can use math factorial of 3, and it prints out 6, okay? If you type factorial of 6, it's not going to return anything. It's going to return an error, because factorial is not defined in Python. It's only defined under the math module. So that's why I do math.factorial. Okay, clear? Now I like this way of typing, calling functions, because it is clear. It is telling you where you're getting the factorial function from. Because it happens there are other modules that define the factorial function as well. So what if you use the NumPy factorial? I don't know if it's there, but let's presume NumPy has a factorial function in it. How do you know which one you're using? You explicitly call the name of the module .factorial. Okay, the reason I say this is that there's another way. If you don't want to type math.factorial all the time, some people will do from the math module, it's really plain English, import the factorial function. What that does, it allows you to use the word factorial or the function factorial without having to refer to the math module. So now I can do this now. Look at that. But the problem here, what if you import another module that has, what if you import all the functions from another module and it happens to have a factorial function? Then you don't know which factorial you're using, it may cause an error. So I would rather be very unambiguous, okay? So my preferred way of doing the programming is to actually be very explicit about what I'm using. So import math, okay, and now we can define the math dot, we can do the math dot factorial. Okay, so to get a warm up, and what many of you may be thinking of doing, you may be inclined to use Python as a calculator and compute each term at a time and then add them all up. Okay, so I'm going to do that in front of you to see that, yeah, this is, one way to kind of get your, get warmed up with using Python, but that's not how we're going to use it. Okay, so it'd be really ridiculous to add up 100 or 1,000 terms that way, because you would have to type a variable for each term, etc. So let's do that. I call that the brute force approach. So let's call it, the brute force. Is there another brute force approach? Okay. And so we're going to do one term at a time. I'm going to define my x as 2, because we want to evaluate e to the 2. Okay, or exponential of 2. Okay, and this is a comment. Okay, it's good to have comments in your code so that you understand what you're trying to do, and if someone else is reading your code, they understand what state of mind you're in, because some variable names I've seen are completely out of this world, but at least the comment would be helpful, to know what you're trying to declare. And so the brute force way would be term 1 is equal to 1, right? So that's term 1. Term 2 is equal to x. Term 3 is equal to 1 over factorial of 2, correct, times x squared. Remember, the exponentiation is you do 2 stars. Okay, x squared, right? So you have 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Okay, and then you could do term 4 is, let me put 1.0 over here, factorial 3 times x cubed. Term 5 is equal 1.0 over factorial 4 times x to the power 4. And then we say our result is equal to term 1 plus term 2 plus term 3 plus term 4 plus term 5. Okay, and then print result. Okay, well, I violated my own philosophy. Okay, so it gave us the value of 7. Just for comparison purposes, I'm going to print the exact value, print exact value, or whatever Python produces, and that's, we're going to call the exponential function that the math module computes, and that has probably 1,000 terms in the Taylor series, or however many, okay, however they compute it, and that will be math.exponential2. So that's what you would get from your calculator, okay? Just to compare, that's the exact value, is 7.38. So you see we're kind of in the ballpark, we're getting there. Now, why did I do this one term at a time? Because I want to be able to calculate the error for each one of those terms, okay? And by the same token, I'm gonna use this approach, the brute force approach, to, I know this is probably looks silly to most of you, but many of you are kind of new to this type of programming, so just bear with me. We're using Python just as a calculator now. Once we're done with this, we're never going to do silly examples like that. Then we're going to hit for loops and while loops and just do thousands of terms at a time, okay? Okay, so what I want now is to calculate the relative, what is it? Where is that? Okay, so I want to be able to generate this table, okay? I want to be able to generate these results. So I need to compute the error for each one of those terms. We said that for the first term, we really don't have an error, okay? And so we have to define the result for each one of those terms, right? So result 1 is equal to term 1, correct? And then for term 2, result 2 is equal to result 1, correct, plus term 2, right? So this would be with two terms, this would be 1 plus x. Okay? Agreed? Those are the two terms. Any issues? Confusion? Okay. Now I can define an error. I'm going to call it error 2 just to stick with the numbering. And that relative error was essentially the absolute value of the current approximation, which is result 2, minus previous approximation, which is result 1. Agreed? This is the current approximation when we have two terms. This is the higher accuracy approximation, and this is the lower accuracy one. So we're going to do result 2 minus result 1 over what? Result 2. Okay? Now, same thing for three terms. The result with three terms is equal to the result with two terms plus term 3. Agreed? So that would add term 1, term 2, term 3. Or you can do result 3 is term 1 plus term 2 plus term 3, whichever one you like. Okay? So then we would have result 2 plus term 3, and then error 3 is again the current approximation, which is result 3, minus the previous approximation, which is result 2 over result 3. Agreed? So let's multiply by 100 to get a percentage. Okay? Same thing with term 4. Now you can see this is repetitive. We're repeating the same thing. We're only changing an index. So we're computing an error. We're calling it error 1, error 2, error 3, error 4. We're computing a result. We're calling it result 1, result 2, result 3, result 4. And that's the power of programming. Rather than doing this repetitive task over and over again, next we're going to just loop over the terms. And we're going to loop over an index, which is going to do result 1, result 2, and 3, and so on for us automatically. Okay? Well, let's finish with this example. So result 4 with 4 terms is equal to the result with 3 terms, agreed, plus term 4. Okay? And then finally, the error with 4 terms is equal to the absolute value of the error of the result or the current approximation, which is result 4 minus result 3 over result 4 times 100. Okay? Let's ditch these two guys. Okay, and let's print the errors. So print error with 2 terms is equal to error 2%. Okay, so I'm just printing, and then error with 3 terms is equal to error 3. And then error with 4 terms is equal to error 4. Execute. Okay. Now, this thankfully reproduced the same values we had in the table. So I told you last time, work out an example by hand for a few terms. Do it by hand. Calculate the error, calculate whatever you're calculating, and then run your numerical implementation for a couple of terms and see if you get the same value. And this is what we got. So things looks like, yeah, we did things okay. All right. Now, obviously, we're not going to be able to do this for 1,000 terms or keep doing it until we hit an error of 1%. We need to automate this process. And this is where programming is powerful. So are you ready to automate this? Okay, we're going to automate it together. And I'll show you how I would think about this. Okay. Okay, so what would be a less brute force approach? The slightly smarter way of doing this. Okay? Okay. So what would you suggest we do? I need suggestions now. Let's see, how would you think about doing this problem? We're doing something that's repetitive. All we changed was, yes. Mm-hmm. Okay. Yes, so that will be our next way of doing it. We're going to start with a for loop. So how would you do it with a for loop? Do you think a for loop would do it? So let's say I want to add a specified number of terms, you know, and that is an option. I want to add 10 terms or 50 terms or 1,000 terms.
You could create an array for the number of terms, like for I in like this array, then like, it could be like 1, 2, 3.
So we need a counter. So let's just create a counter and the size of the counter is specified by the user. So you could come and say, I want you to run the Taylor series for 10 terms, or we want to run it for 1,000 terms. But we're going to keep adding terms until we hit an error tolerance of 1%. Before we talk about the error tolerance, let's just add terms. Add as many terms as we want. So what your colleagues are saying between the while and the for loop is, let's create a counter that counts the number of terms. So we're going to add term 1, term 2, term 3, etc. Or term 0, term 1, term 2, term 3. And we'll use the math formula to essentially implement what we have to implement. So let's remember the Taylor series again. Now, if you notice here, I want you to focus on this formula. This formula is our counter. It is saying this is a summation going from 0 to infinity, so that's your counter. So we can do from 0 to 100, from 0 to 1,000. And the formula is unique. It's 1 over n factorial x to the n. It's very simple. Okay? It's 1 over n factorial x to the n, where n is your counter. So if n is 0, you'll put n equal 0. If n is 1, you'll put n equal 1, and so on and so forth. Okay? So let's go ahead and do that. First, I'm going to define my x. Again, it's x 2.0. And let's just kind of write it in pseudocode. So for counter, going over a number of terms, do something. And what I want to do is calculate this summation. But I need to store the result somewhere, right? So, okay, I'm calculating the summation. I'm adding 1 over 0 factorial x to the 0 plus 1 over 1 x to the 1 and so on. But I need to store those in a result so that I can keep adding and incrementing the result, okay? So let's create an empty variable, is, you know, call it result. Let's initialize it to 0. So this would be our exponential to the 2, e to the 2. That would store the value of e to the 2. We're going to start it at 0, and then we're going to, start adding to it. And I'm going to implement exactly the mathematical formula. 1 over factorial n x to the n. Okay? And I'm going to say result is equal to the previous result. Now, this is similar to what we did before, except I don't have an index anymore. Why? Because the new value of the result is equal to the previous value of result plus that formula, 1 over math.factorial n times x to the power n. Okay. You have questions here, probably? Yes. No. That's pseudocode. That's just my intent. Okay, that's my intent. Now we're going to come back to it because what's missing here, okay, so we know result is, we started result at 0. And so once we enter the for loop, this value, the first time we hit the for loop, this value would be 0. And then we're going to add to it 1 over n factorial x to the n. But what's missing? The value for n. Correct? And n is our counter. Now remember the easy pi slides. How do we create a simple counter? We use what's called the range function. So what I'm going to do, I'm going to introduce the range function here. For n in range going from 0 to, let's say, 100 terms. Now, if you're in doubt, copy this and print it. See what it gives you. That's what it's giving us. The statement for n in range 0 to 100, print n, or for n in range 0 to 10, let's do. Remember, it just gives you a counter. 0, 1, 2, 3, 4, 5. It's just, that's all we need. Because in that summation of the Taylor series, all we need is a counter, okay, to keep adding terms. So now when we come here, For n in range 0 to 100 or to 10, let's start with 10 terms, then we're going to increment our result. Now think about what's happening here. So let's print the value of result before, after entering the loop. Okay, so print result, and I'm going to print it up here first. This is what we get, okay? So the first value of result is 0. The next value, it starts with 0 plus 1, correct? That would be one term, the first term. For n equals 0, that gives you the first term in the Taylor series. For n equal 1, that gives you term 0 and term 1, right? So the indexing is slightly changed because the summation of the exponential starts at 0, okay? And then for n equal 2, 3, and so on, okay? Now, with, 6 lines of code, we were able to do much more than we did with probably 20 lines of code using this approach. We can do, 100 terms. Oops. Does anyone have like a paper towel or a napkin? I spilled some coffee on the... Does anyone have a paper towel, napkin? Yes, Emily. Hey, thank you, Emily. You saved my laptop. No, you don't get an A. You have to work for it. Okay. Okay. All right. What happened to my... Okay, let's just clean up a little bit over here. This always happens. Okay. Looks like... Okay. Okay, so now we're back. We said we did this for loop. Okay, so now this is great, but how do we know when to stop? Now you notice as we print the result, we start kind of converting. Notice that we get to 7.35, 7.38, 7.387, 7.388, and if we do more terms, it's barely gonna change the value. So we've quickly converged to a value that the computer cannot improve on anymore. So if we do 50 terms, just for the sake of illustration, look at that. We pretty much get to a value that doesn't change much more. So obviously, I don't want to run this for 50 values if I can get away by running it for 10 elements, 10 terms. Okay, I don't want to run for 50 terms. So this is where we introduce this tolerance. So to be able to check for the tolerance, what I'm going to do, inside the for loop, I'm going to evaluate the error, the relative approximate error for every term, and then I'm going to say stop once the error is below a certain tolerance. Okay? Clear? All right, so to do that, we need to calculate the error. Okay, I don't want you. Okay. So I can just say, and this is a cool feature of Jupyter Notebooks, is you can use Greek letters. So I'm going to type \epsilon, and then I'm going to press tab, and it turns it into a Greek letter. You can do this with gamma, alpha, beta, whatever, okay? So that epsilon A is going to be my, and again, I'm typesetting here just words in English, okay? Current minus previous, oops, minus previous over current, okay? Now, what is my current approximation? It's result, correct? Now, what is my previous approximation? We don't know, we need to store it in a variable, right? We need another variable to store our previous approximation. So what I'm going to do, I'm going to put here previous, and I'm going to call it, let's say, previous approximation, and I'm going to store the value of the old value of result. So when you think about the for loop, the first time we enter the for loop, the only value in result is this guy, 0. Okay? Then dot dot, we do a new result. Then the next time we come in, it's this previously calculated value that is stored in memory. And so we're going to grab that and store it and hold on to it as our previous approximation. And then we will update the value of result. But what we did here is the old value of result, we stored it in previous approximation. So this would give us the old value. Is this clear? Think of the for loop as you're updating in memory. So once we finish with one entry in the for loop, we have a value for result. That is going to survive once we enter the for loop, and it's going to stay the same until we update it. Think of a location in memory. We haven't touched it. Any questions? Okay. So previous approximation. Oops. Previous approximation. And let's add an absolute value times 100. And now I'm going to print the error. Okay, so obviously some of the keys were impacted by the incident of the coffee spilling on my laptop. All right, so epsilon A percent. It's not perfectly formatted, but let's see. Okay, so this is what we get, kind of unformatted, but look at that. With very quickly, we drop down to an error of 10 to the minus 5%. Okay, so now we can stop. Okay, we can now put a condition and say once the error hits a certain value, we're going to stop. And what was that value in the question? It was 1%. Yes. And so how do we do this? What's the conditional statement in any code, MATLAB, Python? It's an if statement. Okay, and you could say if epsilon A is less than 1%, there's a special word to stop a for loop, and it's called break. And that's essentially saying, hey, break, get out of the for loop. Stop it. Okay? Break. And for the sake of, being on the safe side, I'm going to do this for like 1,000 terms. Okay? Look at that. With how many terms? 1, 2, 3, 4, 5, 6, 7, 8 terms. We hit an error of one. Well, the next term is going to be less than 1%. Okay. And that's one way to do it. Okay. Any questions? Okay, so this is Mortimer the ghost doing its own things. Okay, who did not know how to do this when we started this? Don't worry. Okay. Do you think now you can reason through this to at least know what you want to do? And you want to practice this a lot, okay? So you want to do this for the sine function, for the logarithm function, for other functions, but that's kind of the idea, okay? To automate things, okay? And don't be scared to copy from the internet, to copy, to ask questions, but you have to understand what you're doing, okay? Just like we dissected this problem, there are 1,000 ways to do the same thing with programming, okay? This is just one way. Now, the other way that your colleague over there was talking about, in general, you want to avoid putting if statements inside a for loop. It's really annoying to the computer to every time be doing a calculation and then stop to check something, because it's going to have to exit the registers and memory and do another calculation and then go back. So what we rather do is never break a for loop. Rather, we put the condition in what we call a while loop. Okay, and while loop moves that if statement essentially outside the scope of the for loop and replaces the entire for loop. It becomes a for loop plus a condition, okay, at the same time. And I have the example for that in your slides. I'm not going to do it, we're not going to do it together, but you'll be able to do it. Okay, so this would be the example with a while loop. Okay, essentially, while the error is greater than our tolerance, keep adding terms. And once the error becomes less than the tolerance, it will automatically break. Okay, so I'll leave that up to you to study. It has a similar idea as we did with the for loop, it's slightly more compact. Okay, so I'll leave that up to you to study. And this is the example with the for loop there in the slides. Okay. Okay. Any questions? Yes.
So I noticed that like when you're like doing like the move from like this like for loop, right? So like when you set like your floats, right? So like I tried to like just like the integers, right? So like it works just the same. So like this like Python is like automatically like taking it as a float.
Yeah, but you gotta be careful. Sometimes you may not get. We're gonna hit a problem in iterative methods where you're gonna run into problems if you're only using integers. So if your intent for the number to be a float, explicitly declare it as a float. Put a decimal point next to it. Okay, so that you have no ambiguity. Okay, trust me, when codes get more complicated, you don't know what Python is gonna interpret a certain division as. Okay, and then you may end up in trouble. Now, that's fine if this worked for you, but if it didn't, it would be something to look at. Okay? All right. Yeah. Okay. No reason. I just wanted to start. So what your colleague is asking, if you look at this code, before I enter the while loop, obviously I needed my error to be larger than the tolerance. Okay? Now, what if the reason I chose such a high error is what if I provided an interface for this function that allowed the user to set a tolerance? Then, what I should start at would be a tolerance plus some value, so that I'm always getting into the while loop. But this is just an arbitrary number that I selected. Okay, so we're starting with a very large error, so that once we hit the while loop, while Python is going to say, okay, while error is greater than 1. What is error? It's 10,000. Yes, it's greater than 1. So go in and execute. Okay, but it could be equal to your tolerance, which is 1, plus 1, as long as it's just slightly bigger. Okay. Okay. All right. So here's a summary of the errors we talked about. True error. We talked about true and approximate errors. And in both, we defined an absolute, or in the sense of like, just the real error that's not, or the not relative error, and a relative error. Okay, now be careful again about